In this lecture, we're going to look at production economics. It's important because it parallels consumer demand theory, and the simplest function that we're going to look at is simply this one here, where y, sometimes I'll use a q, is a function of inputs x1 through xn. So the xi's are inputs and y is our output, although at times I'll use q instead. Isoquants are like the indifference curves in consumer demand theory, except that they are cardinal. They actually have a number attached to them, and they're not ordinal. They're just not an ordering, if you like. Some of the production functions that economists use are the following. The Leontief production function, which consists of fixed factor proportions production, all right, as you can see here, and the isoquants is what we call these, but notice that these isoquants are fixed. So you need a fixed amount of Q1 and a fixed amount of Q2, and they have to be in the same ratio. So we can write that function as y is the minimum of alpha 1 x1 dot 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 alpha n xn, where those are the fixed proportions. So think of it as x1 being bicycle frames and x2 being wheels. Then what you'd have is you'd always have one frame here and two wheels to get a bicycle. The more common one that we know is the Cobb-Douglas production function, which is given by y as a function of x, where we have some constant a, and we multiply x1 times alpha 1, x2, alpha 2, etc., where all the alphas are greater than 0, and we have n particular good inputs. The marginal product of any input j is given by the total output, the derivative of the partial derivative of output with respect to xj, and in this case for the Cobb-Douglas production function, it's given by alpha j times q, if you like, or y rather, which is this, which is exactly equal to that, divided by xj. So it's alpha j y over xj, and it has to be greater than 0. And we know that because all the alpha I here are positive. This is a positive number. This is our output y, and input xj is positive as well. And we write that as x greater than 0 because we want to avoid dividing by 0. If we take the first partial derivative of the marginal product of j with respect to xj, or we can write that as second partial of f of x with respect to xj, and we get a very similar result. Here again we have y, but now it's multiplied by alpha j times alpha j minus 1 over xj squared, and that has to be less than 0 if alpha j is less than 1. Notice it has to be less than 1 and not greater than 1. If it's greater than 1, we get increasing marginal product over time, or over that particular input. We draw the isoquants here for the Cobb-Douglas production function as continuously smooth lines where y1, output y1 exceeds output y0. A third production function is what's called the constant elasticity of substitution, or the CES production function, which is given by this much more complicated formula here, beta times in square brackets a1 x1 to the power sigma minus 1 divided by sigma plus a2 x2 also multiplied or raised to the power sigma minus 1 divided by sigma, and then all raised to the power, at least what's in square brackets, to the sigma over sigma minus 1. The average product in this case is given by total output divided by xi, the average product of xi, that is, and the marginal product is the partial of output with respect to xi. The elasticity of output then is given by the partial of f of x, the output with respect to xi times xi over y. Now we know that along any isoquant, if we have two inputs, dy must be 0, so we find dy equals the marginal product times of 1 times dx1 plus marginal product of 2 times dx2 equals 0. From that, we find that dx2 over dx1, which is the slope of the isoquant given by the rise, which is dx2 over the run dx1, is equal to minus f1 over f2. Later, we will show that we define the marginal rate of technical substitution as the negative of the slope of the isoquant. So let's look at the problem from a different point of view, from what we will call the primal, where we minimize the cost, R1, X1 plus R2, X2, where R1 and R2 are input prices, subject to a level of output, a particular isoquant, which is given by Fx1, or F as a function of X1 and X2. We form the Lagrangian, R1x1 plus R2 x2 plus lambda times y minus f of x. Find the first order conditions that are given here with respect to x1, x2, and this lambda. And from the first two first order conditions, we get our result that R1 divided by R2, so the ratio of the input prices is equal to the ratio of the marginal products. Solving these three equations gives us the two input demand functions as functions of the input prices, R1 and R2, and of output. Likewise, the lambda star is given by, and the star of course refers to the optimum. It's a function of R1, R2, and Y as well, and this is called the marginal cost function. Now think about why that would be called the marginal cost function. Well, remember what lambda is. Lambda tells you that if you get a change in this parameter, then it affects the objective function here, which is your cost function. So an increase in 1 unit production of Y that is produced, it tells you by how much the cost will go up, or your cost function. Shepard's lemma then tells us that if we apply it, that the input demand can be determined by taking the first derivative of that cost function that we calculated divided by, the partial of the cost function with respect to input Ri. What are the properties of the cost function? Well, the properties are as follows: that the cost function as a function of input prices and output is greater than 0 for positive input prices and positive output, so non-negativity property. If R prime is greater than or equal to R, then the cost using R prime as your input prices is greater than or equal to the cost if you had your previous prices. So it's non-decreasing in R. The cost function is concave and continuous in R. If we multiply the input prices by T, then it's like multiplying the entire cost function by T, where T is greater than 0, which implies that the cost function is positively linearly homogeneous. If output is 0, the cost function is also 0, so no fixed costs. And finally, if Y is greater than or equal to Y prime, which means that output is greater than some other output, then the cost of producing that higher output is greater than or equal to the cost of producing the lower amount of output. So it's non-decreasing in Y. Let's take as an example the Douglas cost function in log linear form. So in log linear form, we've taken the log of both sides. We get log of C Ry equals a half log Y plus 0.32 log R of labor, 0.28 log R capital plus 0.4 log of the price of M, where XL, XK, and XM are inputs into the production of Y and referred to labor, capital, and raw materials respectively. Shepard's lemma is then used to find the cost minimizing derived input demand functions as follows. So we get the input demand for labor, which is the partial of the cost function with respect to labor, input price, and we get this result here. And we do the same thing for capital and for raw materials. We get these results. And finally, we take the partial of the cost function with respect to Y, the output level, and we get back lambda Ry, which is the marginal cost, and is given by this amount here. Okay, remember lambda is the marginal cost. These equations, these functions, are all derived or are part of Shepard's lemma. So this is important here, that this is Shepard's lemma. The dual, can we use exclusively economic phenomena to reconstruct and study the properties of the technology? So that's the key here. Are we able to use exclusively economic phenomena to reconstruct and study the properties of the technology? And the dual approach attempts to isolate circumstances where this is possible. So in this case, the dual to the minute cost minimization problem is to maximize output subject to a cost constraint given by R1x1 plus R2x2. We form the Lagrangian again this way, but now we're going to change how we denote the Lagrange multiplier. Again, we have this restriction. We find the first order conditions. We find that theta is F1 over R1, where F1, remember, is the marginal product of 1, is equal also to the marginal product of 2 divided by R2, and that's equal to 1 over the lambda, where lambda was our marginal cost. Again, we get the same thing. Ratio of the input prices is equal to the ratio of the marginal products. We also have, of course, our cost function back when we take the partial of the Lagrangian with respect to the Lagrange multiplier. And upon solving, we now get that the input demand functions are a function of the input prices and the level of the cost. Okay, and the same thing with the Lagrange multiplier. So the subscript C here is used to indicate that we're looking at cost as opposed to output entering the input demand functions. Substituting gives the indirect production function. When we substitute these values back into the production function, the objective function, in other words, this is the objective function here, and when we do that, we get that indirect production function, which is a function of the inputs, the input prices rather, and the cost. Now we can look at this in yet another way, and that is by maximizing profit. And in that case, we get price times quantity minus R1x1 minus R2x2, where quantity here, I'm using a Q now instead of a Y, is a function of x1 and x2. We plug the f of x1, x2 instead of the Q. We get this expression taking first derivatives with respect to x1 and x2. Remember, there's no Lagrangian here. And we get that the price times the marginal product of 1 is equal to the input price of 1. Price times marginal product of 2 is equal to the input price of 2. Solving those two equations for P, we get R1 over F1, R2 over F2. And again, we see that it's the value of the marginal product of I is equal to the input price of any I. So again, solving the above three equations for x1 and x2 gives the input demand functions, the derived input demand functions as a function of input prices and output price. Now we can take this result VMPI RI and show that graphically here, where we have the input price here and the output, or pardon me, the input usage on the horizontal axes, and we find that the optimum occurs where that input price, which is fixed at RI star, so we should draw that line straight across at that point. So let me draw that straight across. And this is where our solution lies, where we get the optimum amount of input to use. So if we look back at these derived demand functions here and we substitute them into the profit function, we get the following result, that profit is a function of input prices and the output price, and we call that the variable profit function. We can also substitute the derived demands into the first order conditions, and we do that here. All right, so we get F1 is our marginal product of 1, which then is a function of these of x1 star and x2 star, but we are going to do something with that in a second. So we have these two equations here. We partial differentiate each with respect to R1. Notice we're going to take both equation 1 and equation 2, and we're going to differentiate them with respect to R1. All right. Doing that, we get this result here, where we have this minus 1 because we have the R1 here. We don't have anything here because we're doing it with respect to R1. We're differentiating with respect to R1, and there's no R1 here, so the derivative of R2 with respect to R1 is 0, so there's a 0 there. Now we can rewrite these equations a bit simpler as P F11, where the partial of the marginal product of 1 with respect to x1 is denoted by F11, and the partial of the marginal product of 1 with respect to R2 is given by F12. Pardon me, not with respect to R2, but with respect to x2. So this is the partial of the marginal product with respect to x2. So the marginal product of 1 with respect to x2. So we can write 1 and 2, those two equations like this. We have two linear equations and two unknowns. The unknowns are given by dx1 star with respect to R1, and dx2 star, the derivative of x2 star with respect to R1 as well. So it's these two unknowns that we're looking for, and we're going to solve for. Solving for these gives this result here, 5 and 6. And notice that we have the same denominator in both cases. P times F11, F22 minus F12 squared. We can do exactly the same thing, carry out this same process if we instead take the first order conditions and partial differentiate with respect to R2 rather than R1, and we come up with similar results for dx1 star dr2 and the partial of x2 star with respect to the price of x2. So that we find that here. So 7 and 8 are the equivalent of 5 and 6, but then with respect to R2 instead of R1. Notice that the price cannot be 0 because we can't divide by 0, and this cannot be 0. F11, F22 minus F12 squared cannot equal 0. In fact, for concave functions, F11, F22 minus F12 squared has to be greater than 0. All right, because we have F11 is less than 0, F22 is less than 0, so these two are both negative. Multiplying a negative by a negative, this is a positive number. This is also a positive number. So therefore, as long as F11, F22 is greater than F12 squared, then we find that the input demand curves are sloping down, showing less than sign there. Now we substitute x1 star and x2 star, the derived input demands, into the production function, and then we get the supply function, which is a function of the input prices and the output price. Then we can take that particular supply function and take the partial of it with respect to P to find out whether or not supply is upward or downward sloping. And we get this result here. To get the partial of the input supply with respect to price, both for x1 and x2, we partial differentiate equations 1 and 2 above. All right, these equations way up here. All right, we're going to differentiate those with respect to price. And when we do that, we get somewhat similar results to what we had before, but not quite, because we now have this part here. And when we solve these for x1 star with respect to P and the partial of x2 star with respect to p. We get these two results here. We substitute 10 and 11 into 9, and we find that the partial of the supply function with respect to the price of the good is given by this formula here. The denominator is positive by second order conditions, so this is a positive number. Remember what we said about concave functions. If we have a concave function, then this has to be positive, and we certainly have a concave function here. And the top then, this is positive, this is negative, so this is a positive number. And likewise, this part is positive, and this is negative because of diminishing marginal return, or diminishing marginal productivity rather. And as a result, the numerator is positive as well. The denominator is positive by second order conditions. The numerator is positive because of this result. So therefore, the partial of the supply function with respect to p is greater than 0, and the result is that supply is upward sloping. Finally, recall that profit function, the indirect profit function, if you like, is a function of input prices and output price. If unique profit maximizing supply and derived demands exist, the profit function is differentiable. And then using Hotelling's lemma, remember, refers to an unconstrained optimization, which is what we had. In that case, we can recover the supply function by taking the partial derivative of the profit function, indirect profit function with respect to p, and we can get the derived input demands by taking the negative of the partial derivative of the profit function with respect to any of the input prices to get the input demand function. Other properties of the profit function include that profit is equal to 0. Remember, what happens is in a perfectly competitive economy, there is no excess profit, and that's really what this is referring to. If we have a higher price, p prime greater than p, then the profit function is greater than what it would be at the lower price. So it's non-decreasing in p. So in other words, the higher the price, the more profit. If input price is greater than the original input price, then the profit function is less than what it was previously. And the profit function is both concave and continuous in our input prices and output price. And finally, the profit function, if we multiply all the input prices and the output price by t, it's the same as multiplying the profit function by t, as long as t is greater than 0, and that is a positive linear homogeneity property. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.